Greetings. My name is Dr. Benjamin Prather, and today I want to give a little talk about basically what I would discuss with my calculus students on the first day of an AP calculus class. And the main thing I want to look at is there are two main operations that we deal with in calculus. And the first one is what is a derivative, and then what is an integral. And then I want to look briefly at how are they related, because one of the main themes that I plan to do next year especially is to talk about how calculus is, the calculus steps are easy, the concepts of calculus are easy, it's the algebra and that really gets tricky. And so if we can get the calculus concepts down, then we can review our algebra concepts and make sure those are where they need to be. And then that is probably one of the better ways to approach calculus. So with the AP course going to now where they allow Desmos, it seems like if we're going to introduce calculus, visual is a very good way to approach calculus with the visual media. So I'm just going to go straight to where we're going to log into Desmos and get rid of this picture because nobody really wants to look at that face for a whole video. And we're just going to look in Desmos. And I strongly encourage you to open up Desmos on your own and pause this video as you need to go. But the idea is, if I were in front of a classroom, I would ask my students for, give me a function. Give me an example of a function, and maybe they'll give me a linear or quadratic function. I'll ask for something more exotic, and so they'll give me something cubic, like maybe f of x is equal to, maybe a cubic, because if linear and quadratic are not good enough, and then maybe someone will give me a 9x squared, and probably somebody's going to give me a 6, and then the next person is probably going to give me a 7. Now, that's a little bit hard to see on this default graph on Desmos. So I might then say, okay, that's good, but I'm going to go in here and condition this function a little bit and put a parenthesis there, divide by x to the 4th plus 1. That's not enough, maybe 2. All right, there we go. So that gives us a nice little function with a couple of bumps in it. And one thing right off the bat that is useful for Desmos is if you just mouse over one of these points, so hopefully you can see that little dot for that pen. If you mouse over here, it will give you your intercepts. You just click on it, and then you have your intercepts right there. And then if you click anywhere off that screen, you can come back, and if you actually click on these maximum points and it grays them for you, so if you hit near those gray points, right away, if you have Desmos, you can find your x and y intercepts, and you can find all of your maxima and minima. So that is a useful thing to do. So what we're going to be learning in calculus is, by the end of the year, hopefully, know what's going on under the hood a little bit, that what is it that Desmos might be doing to find those extrema. All right. But suppose I wanted to make a point. Another thing Desmos can do real quick, so I can add a point on the function. And I'm going to say a, that's just what a particular x value. And in the graph, the point a f of a. And then if I add a slider for a, that will now give me a point. And now if I come in here and move that slider back and forth, I see that that point slides right along the function. So there we go. And that makes sense because I've got a and I've got f of a. So that is the xy coordinate for x is equal to a and the corresponding y value. Hopefully nothing surprising there. Now, if we recall from algebra, in order to get a line through a point, we can use the point slope formula. Y is equal to m times x minus my initial value, which since we have that point a, f of a, we might as well use that. And then we can add our f of a. Now, for now, I'm going to add a slider for m. And I can actually click this animate button, and then a will go back and forth. Why is that not animating? A can go back. That seems like it's going a little bit too fast, so maybe slow that down a bit. And now I can see I've got that point going through, and I've got that line. And maybe I can try sliding that m back and forth to try to get that slope, but that's going to be a little bit tricky to keep up with the animation. So it would be nice if we had a mathematical way in order to get the derivative or the slope at each point. And I gave away where I'm going because the calculus concept that gives you the slope at a given point is called the derivative. And we don't need to know right now for what it is. Right now, I want to emphasize the concept. The derivative is literally just the slope. So if I come in here and I replace that m with this little prime, means to take the derivative of x and then evaluate it at a, because I put a in there instead of x. And now I can see that that tangent line at every point, it actually is making a tangent line because it now knows what the slope is. So what is the derivative of a function? It is literally just the slope of that function on the xy curve. A related concept is if we were dealing with time instead of x, and we were dealing with some quantity, then the derivative would be the rate of change. And the rate of change is just the slope. The average rate of change is just the slope function. And then that is how we get the derivative also applies to rates of change. So that is the first of the big calculus concepts, is that the derivative is just a word for the slope of a function at every point. So we have a function, we get a new function that gives me the slope of that function at every point. We'll be far more precise about this when we get into how do we actually find derivatives. But with Desmos can find the derivatives for us. All right. So the second trig function, not trig function, main calculus function is the integral. So let's make an area on here. So suppose I want to shade in the region where 0 is less than or equal to y is less than or equal to f of x. So that's the whole region. But maybe we only want that for the region where -8 is less than or equal to x is less than a. Since we got that a slider on there, let's go ahead and find that. So we got this area going back and forth. So we're shading in this area. It'd be nice if we had a way to actually find this area underneath this curve. And it turns out that in calculus, that is what the idea of an integral is. If the function is positive and the a is bigger than that -8, then the area between the curve and the x-axis is just what the integral is. We'll define it more precisely later, but that is the concept that we're trying to make the integral be. And for the integral, we have this weird extended s because it's viewed like a sum. So it's going to go from -8 to a. So those bounds there just tell me what are the left and right endpoints of the area that we're looking at. And then this dx is just like a closing parenthesis that tells me, so this extended s with the bounds is like an opening parenthesis, and a dx is like a closing parenthesis that says find the area of whatever function I put in there. And right now it's just finding the area of, well, the function 1. But if we really want to, we can say f of x dx. And now we can see the area is going through. I'm going to pause that here in a minute when it gets somewhere closer to here. Oh, I didn't pause it. It's not pausing. Why are you not pausing? All right, I'm going to pause it. All right, if I just slide to A, it pauses. Now I'm going to put it, let's go ahead and put it right here at 0. So if I put it here at 0, then I can see that most of the area is right here between -2 and 0. In fact, if I chop this off, it'll fill in those regions, and it looks like it'd be about a total of 6. And when I look here, that looks about right, because 2 times 3 is 6. Apparently, I'm off by a little bit there. And then if I move this A slider over here, to -2, I can see that, well, this region here looks like 1, maybe borrow a little bit, and then there's like maybe another half right in here, because each of these tick marks is really a quarter. So there's another half right there. So it looks like it's going to be about 1.5, and it looks like that estimate's even better. And then if I come over here to 4, I can see that, well, if I chop this part off up over there, it'll probably fill up over there. A lot of this tail will probably fill up most of there. So it looks like it would be about, that base is 6, that height is 4, so it looks like it'd be 6 times 4 is about 24. And again, that's just a rough estimate, so I can see that I slightly overestimated a little bit. If you actually tried to count up these little squares, how many of these little squares there are, you could probably get a better estimate. But that is basically the idea of an integral. So a derivative is just a slope at a given point, and the integral is just the area between two endpoints underneath the function. So those are the two main concepts of calculus. The rest of the year would be spent discovering how to find these things and how to use these in applications, what makes them useful. And at first, these two concepts do not look like they're going to be related. They look kind of like completely different things. How do slopes and areas relate to each other? And it turns out that if this function that we're finding the area underneath is itself a rate of change, we'll be finding out later in the class that if you integrate a rate of change, that will tell me the total amount of change. So the surprising, remarkable fact, and what makes calculus one of the central facts of calculus, that even makes computing with calculus possible in some cases, is the idea that these two operations of taking the slope and finding an area are inverse operations. And this is so remarkable, it's called the fundamental theorem of calculus. So already in this first introduction, I've introduced you to the derivative. It's just the slope at the point. I've introduced you to the integral, which is just the area underneath the curve, and the fundamental theorem of calculus, which is that these two operations are going to turn out to be inverse operations of each other. I hope you've enjoyed this video, and I'll be hoping to make more in the future. Thank you for your time.